Substances and solutions, their property. Alright, this section starts off talking about formula mass, which is really pretty simple. You simply add up the weight of everything that's inside of a compound or a formula. So water has 2 hydrogens and 1 oxygen, so I would add up the weight of those 2 hydrogens plus the weight of that 1 oxygen. That's its formula mass, the grand total. Alright, so the book uses this example, CHCl3. Well, I got 1 carbon, 1 hydrogen, and 3 chlorides. So I would just add those up. 1 times 12, 1 times 1, and 3 times 35. Add all that up, 119.37 atomic mass units, AMUs. That's the formula mass of CHCl3. Now, where did these numbers come from? Where did the masses of the individual atoms come from? The periodic table. If I pull that up, here's hydrogen, 1.0079, and here's carbon, 12.01, and chlorine is 35.43. So that's where you're going to find the numbers for the individual masses of those atoms. Remember, those are averages of those isotopes, but that's exactly what we would expect those molecules to be made up of anyway. So adding up the parts, that works just fine for both covalent and ionic compounds. Now for covalent compounds, because they actually come as molecules, sometimes it's called the molecular mass, right? Which is fine. But for ionic compounds, they don't come as molecules, they come as crystals. And so really formula mass is the right word for that. And let me show you what I mean by that. Here from the textbook, here is the molecule for a covalent compound, the one that we just looked at, CHCl3, and it's these 5 atoms. They're all bound together and they come as a unit, and so that molecule. Here's another larger one, that's aspirin. Here's another one, this is acetaminophen. So this is ibuprofen, and so it's a molecule. But if I scroll down here, now here's sodium chloride. It's not a molecule, is it? It's an extended crystal of positive and positive, negative, going back and forth and back and forth, right? But what do we write for sodium chloride? We write NaCl, 1 sodium, 1 chloride. And so that's its formula. It doesn't come as a molecule, and so we should technically call it the formula mass. Now you'll hear, maybe we get a little sloppy sometimes. We always call it molecular mass, but technically that's wrong. We should stick to formula mass. Alright, so let's see, in the book there's a couple additional examples here, 3.1 and 3.2. So let me scroll back up here. Here's 3.1. Again, ibuprofen, big molecule, right? But if you look at the formula of it, C13, H18, oxygen 2. All right. 13 times 12, that's my 13 carbons. 18 times 1.008, that's my 18 hydrogens. And 2 times 16, those are my 2 oxygens. Add them all the way up. 206.27 AMUs, atomic mass units. So big ones, no problem. We just add them up anyway. Okay, example 3.2. Here's an ionic one. Well, same idea. It may be a repeating crystal, but here's the formula, Al2SO43. Now this is a little different because you have this polyatomic ion, but don't let that fool you. I've got 2 aluminums, so 2 times the weight of an aluminum. I've got 1 sulfur here, but then there's 3, as you can see, 3 of those sulfates. So there's really 3 sulfurs. 3 times 32 right there. And then here the oxygens, there are 4 of them, but again I've got 3 of the entire sulfates. That's a grand total of 12. And so that's why they're multiplying 12 times the weight of the oxygen. Add that up. Ooh, big one. 342.14 is its formula mass. Alright, with that under our belt, now we're ready for the concept of the mole. The mole is the SI unit for the measurement of an amount or a counting of something. Just like the SI unit for weight is, or mass I should say, is gram. And then you've got kilogram. Actually kilogram is the base SI unit, but let's see, liter for volume, all those guys. So the SI unit for counting something is the mole. Now if I was counting donuts, I could tell you, hey, I've got 24 donuts. Or I could tell you, I've got 2 dozen donuts. I'm telling you the same thing because we know that a dozen means 12. That's a unit of counting. If I say I have 3 dozen, you know that means 36 because every 1 dozen is worth 12. Well, what about a mole? How many is a mole worth? Well, the number there is an Avogadro's number. He's even got his own number, right? Avogadro. And that number is huge. 6.0221 0.4179 times 10 to the 23rd power. So that's massive. It's a huge, huge, huge number. But that is how many things are in a mole. Just like 12 is how many things are in a dozen. Or maybe 2 is how many things are in a pair. It's just a number. It's just a number of counting. Now, why do we use such a huge, huge number? Well, when we're talking about very small molecules and very small atoms, and yet we're going to be weighing these things out in the lab, there's going to be a lot of atoms, a lot of molecules, and so it does make sense that the unit that we might use is a pretty big number. Now, why didn't they just make it 1 times 10 to the 23rd? Well, they actually based on carbon. Right? They didn't just pull any number out of the air. The Avogadro's number is technically the number of carbon-12 isotopes, atoms that is to say, which would be required to weigh exactly 12 grams. Okay, so carbon, number 6 on the periodic table, if there's the most abundant isotope has 6 protons and 6 neutrons, so that's carbon-12. So the most abundant one for carbon. All right, and here's the idea. If you had a scale and I kept throwing atoms on, here's another carbon-12, here's another carbon-12, and I just kept on going and going until that mass comes up to exactly 12 grams. All right, and I'm counting them as I go. How many atoms would it take? The answer is Avogadro's, 6.0221. So we actually define Avogadro in terms of carbon-12. Just like we defined the AMUs in terms of carbon-12 as well. Remember we said one carbon-12 atom weighs exactly 12 AMUs. That's where we got that definition of AMUs from as well. Okay, so a mole, 6.0221 times 10 to the 23rd of whatever I want to count. Atoms, molecules, donuts, it doesn't matter. It's just a counting thing. Okay, and again, it's got its own name even. That name is called Avogadro's number. Which brings us to this idea now of molar mass. Molar referring to a mole of something. So molar mass is how much weight does something if I have a mole of it. Again, as opposed to if I have a dozen of it or something like that. Now, of course, a mole is a lot of it, a very big number, right? But nevertheless, if I had a mole of some substance, how much does it weigh? Throw it on the scale. That would be its molar mass. Right? And here's a picture from the book, Figure 3.6, which shows you what 1 mole of various things look like. So in the back there, let's see, we've got octanol, a liquid, an organic liquid. It's got that much volume, you can see. Over here, that's mercury 2 iodide, reddish powder. Well, that's 1 mole of it right there. Up here, that's ethanol, or methanol, excuse me, methanol, wood alcohol. Not as much. This looks like there's more of it here, less of it here. Well, volume-wise, but again, it's 1 mole if I counted how many molecules there. And then here, sulfur. Sulfur comes as S8, the S8 molecule, and that's how much 1 mole of sulfur looks like. Right? And you can see in the legend here, they've even added up what the weight of all those various things are. Again, based on just adding up the formula mass and then taking 1 mole of it. All right. If you look at this table here from the textbook, they're just going down. What does 1 mole basically weigh? So carbon, all right, different isotopes, but the average is 12.01. That's it. And again, if I take 1 mole of it, that weighs exactly 12 grams. But if I take this mixture of isotopes, it would weigh 12.01 grams. Oh, so in other words, that 12.01 on the periodic table is how many grams 1 mole of that atom, that element, would weigh. Right? Again, how many molecules is that, or how many atoms? An Avogadro's number. Right? So if I'm looking at this periodic table, like beryllium here is 9.0122. I can think of that as AMUs, atomic mass units. I could also think of it as, if I had 1 mole of beryllium, how much would it weigh? Well, 9.0122 grams, the number that's right there on the periodic table. Right? Iron, if I had 1 mole of iron, 55.847. So these numbers are also not just AMUs, but they're also grams per mole. Right? Again, if I had 1 mole, how much would it weigh? So grams per mole, and all of these numbers can be thought of that way. Neon, 20.179 grams per mole. And that's a really important concept. The idea that an AMU and a gram per mole are the 2 different ways you should interpret those numbers on the periodic table. All right, so example 3 from the textbook. Let me pull that up here. Example 3 says, or asks, says, according to nutritional guidelines from the USA Department, blah, 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 an estimated average of potassium is 4.7 grams. All right, potassium, 4.7 grams. Estimate the average requirement in moles. So in other words, how many moles are in that 4.7 grams? Okay, here we start off, 4.7 grams of potassium. I'm asked to convert that to moles. How many moles would that be? Well, if I go back to my periodic table and I find potassium, there it is, 39.102 grams per mole. And so I want to use that 39.10, and the book rounds it off a little bit, and that's fine. I'll go ahead and follow their lead. I want to use that grams per mole. See, I'm using that as a factor, as a conversion factor, where I'm trying to convert 4.7 grams of potassium to moles of potassium. That's exactly what those numbers on the periodic table do. All right, so put grams on the bottom. That way it'll cancel with the grams over here. Moles goes on top. All right. The numbers from the periodic table, 39.10 grams is what 1 mole weighs. All right, so there's my 1 and my 39.10. And then multiply it and divide it as usual. 4.7 times 1 divided by 39.1 equals 0.12 moles. Alright, so that many grams of potassium is 0.12 moles. If you could count them, that's how many potassium atoms there would be. Alright, let's look at the next example. A liter of air, 9.2 times 10 to the minus 4 moles of argon. Alright, so air is a mixture of different gases. They say, hey, if you have a liter, you know about the size of a liter, you know a 2-liter bottle, right, of soda, so half of that, a liter of air, that's how many moles of argon would be in that. And they say, what is the mass of that argon? What is the mass? So I'm trying to convert moles to mass, which be grams. Moles to grams, hey, again, that's off the periodic table. I look at my periodic table. Here's argon, 39.948 grams per mole. Grams per mole. All right, and so let's set that up. 9.2 negative 4 moles of argon. I'm putting moles on the bottom this time, so it'll cancel. Grams goes on the top. And notice I'm writing not just moles, but moles of argon. Grams to argon. Always write both the unit and what it is you're talking about. All right, so you don't get mixed up, and that's going to be really important later on in just a chapter or two. All right, the numbers, 39.55 grams of argon in 1 mole. Multiply, divide by 1. 0.037 grams. So if I weighed out that argon in 1 liter of air, that's how much it would weigh. All right. One last kind of important example here. The next one, 3.5. It says here, shows some copper wire. How many copper atoms are in 5.00 grams of that copper wire? So they're asking not for moles, but actual atoms. Actually, give me not moles. It's the difference of saying how many dozen donuts or just how many donuts. Right? I could say there's 3 dozen donuts. The answer is 3. Or I could say there's 36 donuts. Right? 36 would be the answer there. And here, they're not asking for moles. They're actually asking for how many atoms themselves. All right, so we set that up. 5 grams of copper from the periodic table. Pull that up. Copper weighs, here's copper, 63.546. All right, so I put grams on the bottom, so it'll cancel. Moles on the top. All right, 63.55. All right. Now I've got moles of copper, but I want to go to atoms of copper, not just moles. And so I got one more step. I'll put moles of copper on the bottom, so it cancels. Atoms of copper. And how do I know what number to put in here? Well, a mole of anything, I don't care if it's copper or aluminum or hydrogen or donuts, a mole of anything is Avogadro's number, 6.0221 times 10 to the 23rd. Again, just like a dozen is 12. I don't care what it is. A dozen is defined as 12. Well, a mole is defined as 6.0221 times 10 to the 23rd. All right, so I put those numbers in. Again, moles is on the bottom, so it cancels. Atoms on the top. Once I get here, I can go ahead and pick up my calculator and put it through as usual. So 5 grams divided by 63 times Avogadro turns out to be a pretty big number. Not surprising, right? 4.74 times 10 to the 22nd atoms of copper. All right, so we've done the concept of a mole, formula mass, and how to convert back and forth.